Okay, so now we've had a look at some of the principles about Kc. I hope you've managed to go back through your notes and sort of consolidate your understanding of how we write Kc expressions. And in this video, we're going to be having a look at how we might use the data we're given in an exam to be able to work out a value for Kc. So you'll find the notes for this in Kc Screencast 2 in the Equilibria folder. And what I would say is that you can open this document here. Okay, if you just double click, it will open up a Word document that you can fill in your own, or alternatively you can do this handwritten into your notes as well. So you will find a blank copy of the questions there. So we're going to have a look at this question. I'm going to talk you through how I would answer it and sort of model my thought process and some of the things that we need to take account of. So compounds A and B react together to form an equilibrium mixture containing compounds C and D, according to the following equation. And if you remember from my previous screencast, I would always highlight the balancing numbers because we know that they are important when calculating Kc. Now, a beaker contained 40 centimetres cubed of a 0.16 mole per decimetre cubed aqueous solution of A. So by identifying the fact that this is a volume and this is a concentration, okay, we're going to need to calculate the number of moles, because when we are working out these questions, we're often asked to work out the moles of particular substances equilibrium mixture, which is exactly what we're being asked to do in this question here. So here I've got a volume and I've got a concentration. I've got 9.5 times 10 to the minus 3 moles of B and 2.8 times 10 to the minus 2 moles of C. And we don't know what the number of moles of D are, but if we put some A and some of B and some of C in, and we've put nothing of D in, then we can assume that we have 0 moles of D at the start. Okay, D is a product and it has yet to be produced. C is also a product, but remember this is a reversible reaction, so once the system has reached equilibrium, the forward and reverse rates of reaction will be happening at the same rate. The equilibrium mixture formed contained 3.9 times 10 to the minus 3 moles of A. Calculate in moles B, C and D in the equilibrium mixture. Now I'm just going to bring, so perhaps you've opened this document so you can still see the notes. I'm just going to bring it across here so we've got plenty of room to do some working out. Now, when we're setting up these questions, I would always write the expression at the top. So here I've got 2A plus B, reversible reaction to form 3C plus D, and again highlighting my balancing numbers. Now we are asked to work out the number of moles at equilibrium, and we are given moles at the start. So if you remember though, we do need to work out the number of moles for A because we've only been given its volume and its concentration. So we know according to the equation N equals C times V over 1,000, and we do need to divide by 1,000 to convert into decimeters cubed because we've been given 40 centimeters cubed. So we'll have 0.16 times 40 divided by 1,000, and that gives us 0.0064 moles of A at the start. So I can then input that into this number here, so 0.0064. Remember, as you carry across from your calculator onto the page, make sure you're giving it to the right number of decimal places. We've been told that we've been given 0.0095 moles of B, and we've been given 0.028 moles of C, and remember we've got 0 moles of D because there was nothing put in there at the start. Now we've been told that at equilibrium we have got 0.0039 moles of A, and we don't know the number of moles of B, we don't know the number of moles of C, and we don't know the number of moles of D. But we can use the information that we've been given both in this equation here and the information we've been given about the number of moles present at equilibrium to work out these concentrations. Now, first of all, we need to work out, okay, well, how many moles has A gone down by? So to work that out, we're going to do 0.0064 minus 0.0039, and we're left with 0.0025. So there's a difference there of 0.0025 moles of A. Now, the most important thing here, before you work out how much B has gone down by, remember, if A and B are reacting together, these are both going to be going down, whereas the amounts of the products of C and D are going to be going up. So we're going to put a minus sign there and a plus sign there. So I just highlight those to make that nice and clear. Okay, so this is where our ratios become really important, because we've got a 2 to 1 to 3 to 1 ratio. So if this is a 2 to 1 ratio, we're going to assume that B has gone down by half as much. Okay, so we can see then that B will have gone down by 0.00125, okay, giving us 0.00825 moles of B. Similarly, C has gone up by a ratio of 3 essentially. Okay, now we know what a ratio of 1 would be. We can say, okay, well, it's going to go up by 0.00125 times 3, okay, which is equal to 0.00375. So if we add 0.028 to 0.00375, we get an answer of 0.0318. Okay, and we've gone from 0 moles, and this is a 1 to 1 ratio. You can see now that we're using a ratio of 1, that's gone up by 0.00125. So our answer there would be 0.00125 moles. And there we have calculated the number of moles of B, of C, and of D at equilibrium. Perhaps you'd like to pause the video now and to sort of go through that in your own mind. And I'm going to continue with part B of the question. So let's put our answers there. And you can often assume that in these questions, you will have to use your answer to part A to perhaps answer some questions later on. May or may not. In this case, you don't, but it's often worth noting that they do ask you to carry this forward. So give the expression for case C and its units. Do not forget to answer both parts of the question, and this is only a 2-mark question, so they assume that this skill is perhaps relatively easy. So let's go back to our expression, 2A plus B to 3C plus D. So we've got concentration of C to the power of 3, oh, not plus, multiplied by concentration of D divided by concentration of A to the power of 2 multiplied by the concentration of B. So there's our Kc expression. Okay, that's our first mark. And then we need to calculate the units. Again, not forgetting to do the second part of this question. So the units are equal to mole per decimeter cubed, power of 3, multiplied by mole per decimeter cubed over mole per decimeter cubed to the power of 2, multiplied by mole per decimeter cubed. And we know when we do this, we need to add the powers first. So we've got mole to the 3 plus mole, so we've got mole to the power of 4. Now we've got minus 9 here because we're multiplying these numbers, add another minus 3, so that's to the power of minus 12, divided by mole to the 3, okay, because we've got 2 here and 1 here, and then that's going to give us -6 and another -3. Okay, so that's going to give us dm power of -9, and then remember we subtract them to simplify this expression, so that's going to give us mole, because we've done 4 minus 3, which gives us 1, minus 12, minus -9, so adding -9 is going to give us -3. So there are our units of Kc. There's your 2 marks there. Okay, so now we move on to part C. A different equilibrium mixture of these 4 compounds at a different temperature. So remember, Kc will be different, okay? Well, Kc has been affected because temperature does affect Kc. Contains 0.21 moles of B, 1.05 moles of C, and 0.0076 moles of D in a 5 to the power 10 times 10 to the power of 2 centimetre cubed solution. And they've given you what the value of Kc is here. So what you're asked to do now is calculate the concentration of A in mole per decimetre cubed. So here we're going to have to do a bit of rearranging, and it is worth that you practice a question such as this. So the first thing that we need to remember here is that they're asking you to calculate the concentration of A. They're not asking you to calculate the number of moles. However, you have been given data about B, C, and D in moles and not concentration. And when you calculate Kc, or when Kc was calculated, okay, concentrations were used and not moles. But luckily, you have been given the information that you need to calculate concentration because you've also been given the volume. Now, we know that concentration is equal to n times 1,000, so the number of moles times 1,000 divided by volume, unless we convert our volume into decimeters cubed. And this is what I would do in order to sort of simplify some of the working out that you're going to have to do when you're using your calculator. I'm going to show you how I would do this and how I would lay it out. You may want to do it in more stages than this, however, I believe that this will keep sort of your answers to a better degree of accuracy. So what I would first write down is the Kc expression, okay, or I'd refer to it as I've just done it up there. So we know that because this is for the same reaction, so Kc is equal to C to the power of 3 multiplied by D divided by A to the power of 2 multiplied by the concentration of B. I'm going to highlight in green everything we know. We know this, we know this, we know this, we know this. We don't know what A to the power of 2 is, okay? So our question is find the value of that. Now, I'm going to put my numbers in here, and this is just the way that I work. Remember, you might work about it in a different way. But I know that the concentration, I know the value of Kc is 116. So let's transfer our knowledge from this part here in over here. So 116 is equal to the concentration of C. Well, we know that the number of moles of C is 1.05. So if 1.05 moles of C, we need to convert that to a concentration. We could say that the concentration is equal to the number of moles divided by the volume if we are putting the volume in to decimeter cubed. So that would give us 1.05 divided by 0.5, okay, because 500 centimeters cubed is equal to 0.5 decimeters cubed, okay. This is exactly the same as saying C equals n times 1,000 over V, okay, which would just give us this. However, I'm taking out this sort of multiplying by 1,000 step by originally converting my volume into decimeter cubed, because when we come to put it into this expression here, you'll see it looks simpler than adding in your times by 1,000. So 1.05 divided by 0.5, and that's to the power of 3, multiplied by the number of, or again, we're going to calculate the concentration of B, so we've got 0.076 moles divided by 0.5, so that's going to give us our concentrations of C and D, divided by, again, we don't know the concentration of A, okay, multiplied by the concentration of B. So this step here, okay, I've written my Kc expression and calculating the concentrations of what I do know, so of B, C, and D. So if I put these numbers into the calculator, okay, and I did that separately, so 116 is equal to, and I did this top line all together first, okay, so that gave me a value of 1.407672 divided by, again, we don't know what a to the power of 2 is, multiplied by 0.42. So you might see now how I simplify the expression, so I'd multiply 116 by a squared, okay, so 116 times a to the power of 2, okay, is equal to 1.407672. Again, being careful, I'm copying the numbers down from the calculator correctly, okay, divided by 0.42, okay, and I worked out that value there. So that gave me 116 times a to the power of 2 is equal to 3.3516. Now, we can see how we can make a squared the subject of the equation by bringing 116 to divide by here. So our next step would be a squared is equal to 3.3516 over 116. So we therefore must say that A, or the concentration of A, is equal to the square root, because we get rid of this square here, of 3.3516 divided by 116. And if you put that value into the calculator, which I'm just going to do now, you come out with a value. I'm just going to write what I've got on my calculator here, 0.169979714. Now that number is obviously far too long to give as your answer, and the question says give to the appropriate number of significant figures. Now we know from previous work and calculations that the accuracy of our final answer must be no greater than the least accurate measurement. Okay, we cannot just assume a greater accuracy. So let's go back to the question over here. Okay. Now we've got 0.21 here. So it's 2 significant figures, 3 significant figures, 2 significant figures, 2 significant figures, or 3 significant figures there. So our least significant figure is 0.21 or 0.0076. Therefore, we can only give our answer, okay, to 2 significant figures. So rounding this to 2 significant figures here would give us a value of 0.17 mole per decimeter cubed. Now, I appreciate there's a lot there, so perhaps it'd be worth going through that calculation again and pausing the video where necessary, and then perhaps giving it a go in your own time to see if you can recreate that thought process. Okay, good luck.